Do you remember 6 degrees of Kevin Bacon? It's a classic problem in graph theory, and there's a website that will generate Bacon graphs for you. Kevin is a vertex, and he's connected via edges to people he has worked with. Kevin is connected to Tom Hanks because they appeared together in the movie Apollo 13. Tom is connected to Rob Reiner because they were both in Sleepless in Seattle. Rob is connected to Jonah Hill because they were in The Wolf of Wall Street. Jonah is connected to Paul DePodesta because Jonah played a character based on Paul in the movie Moneyball. And Paul is connected to me because we both spoke at the same technology conference. Italian Americans like Paul and I talk with our hands a lot. But what the heck was I talking about when this photo was taken? It was either the binary number 0 or how to drink a milkshake. The computation of a Bacon number is a shortest path algorithm applied to a network. Tom Hanks' Bacon number is 1 and mine is 5. The 6 degrees game can be applied to any graph, including graphs about technology innovation. For example, Sergei Korolev was the Soviet Union's chief rocket scientist. His Sputnik satellite traveled around the Earth 60 years ago, an event that shocked American scientists. To put some perspective on this, it was a really small satellite, but it still caused big fear in America. Here's some more perspective. This took place in the 1950s during the Beat generation. A few months after the launch of Sputnik, the word beatnik was coined. Crazy. President Eisenhower had to do something about the Sputnik crisis because Americans feared the technology gap between us and the Soviets. So 59 years ago, he created ARPA to ensure that our technology would be better than our enemies. Enter Joseph Licklider, the first director of ARPA's IT department. 54 years ago, he came up with the concept of an intergalactic computer network, which described features similar to today's internet, but with a much cooler name, intergalactic. Glenn Culler was the director of the Computer Center at the University of California in Santa Barbara. 48 years ago, his interactive computer system was chosen to be one of the first 4 nodes on a version of the intergalactic network named ARPANET, which would later become the Internet. When ARPANET launched, Glenn's son David was 10 years old, and he was fascinated by his dad's work with computers. David grew up to chair Berkeley's computer science department, and he helped teach this graduate course 8 years ago. Along with homeworks and exams, the course required a term paper or a project. Matei Zaharia was a student in David's class. For the project requirement, Matei built a cluster manager that could treat an entire data center as if it were one giant computer, and he named the project Mesos. Later, he wanted to demonstrate how easy it was to build a new framework on top of Mesos, so he created Spark, which is now the most actively developed open source project. Therefore, Spark's Sputnik number is 5. So if I'm an emerging technology guy, why am I talking about old stuff today? As Rome's Cicero once said, to be ignorant of what occurred before you were born is to remain always a child. Or, if you prefer the classics, you never know where you're going till you know where you've been. I was gonna wear that shirt today. Let's take a journey back through the decades, starting with the 1930s, when the probability of a major war led to investments in technology. Just to level set, this newspaper ad shows an example of innovation in the 30s. So technologically, the 1930s were like the Stone Age. This is not a prison photo. This is Claude Shannon's undergrad class photo. During an internship at Bell Labs, this boy genius had an epiphany about Boolean algebra, and he used this idea for his MIT master's thesis. You're going to hear me say Bell Labs and MIT a lot today, so every time you do, take a shot of coffee. Shannon was only 21 years old when he authored one of the most important theses ever written, which proved that electric relays could implement the concepts of Boolean algebra, a revelation that led to the creation of digital circuits. Speaking of Boolean algebra, the goal of George Boole's first book was to use algebra to prove Aristotle's logic. So if we follow the edges from Boole to Shannon to digital circuits, computing devices like your iPhone were made possible by math equations created 170 years ago. Oh, and yes, I was talking about that Aristotle, the student of Plato and the teacher of Alexander the Great. What George Boole called logic, Aristotle would have called analytics. So you can trace your iPhone's lineage back 2,300 years to Aristotle's analytics. George Stibitz worked at Bell Labs, and he built the first digital calculator using telephone relays, batteries, and 2 flashlight bulbs to represent the numbers 0 and 1. This proof of concept with binary arithmetic laid the groundwork for digital computers. The 1940s saw the first use of computers during a war. Again, to level set, innovation was still prehistoric, especially for consumers, as seen in these 2 newspaper ads for healthy baby sun lamps. 70 years ago, MIT designed a computer named Whirlwind for the Navy. Its original purpose was to operate a flight simulator to train bomber crews. But MIT students also used it to create one of the first computer games. Video games had a surprising effect on innovation, and we'll see an example of this later. MIT invented a new technology for Whirlwind called magnetic core memory, which contained small donut-like cores that were strung together by hand into a grid. Each core stored a bit, magnetized one way for 0 and the other way for 1. The wires could both detect and change the state of each bit. This panel contains 1,024 cores, so it can store 1,024 bits, which is 128 bytes. Panels were connected together inside a telephone booth-sized unit which could hold 2,048 bytes of data. Whirlwind was also one of the first computers to calculate in parallel. So let's take a break from the 1940s and look at some examples of parallel processing. The first known written use of the term computer was from 400 years ago, and it meant a person who computes mathematical calculations. Galileo was a computer. A room full of people could solve a long calculation by dividing it up so that it could be computed in parallel. Before Whirlwind, computers operated 1 bit at a time. This is a page from the actual user's guide. Whirlwind contained 16 math units, which processed a complete 16-bit word every cycle, making it 16 times faster than other machines. These reference cards were used by programmers of Teradata's first machine, the DBC 1012 database computer. Even though the concept of a relational database was conceived 15 years earlier, computers weren't powerful enough to run really large relational database management systems. Therefore, Teradata advertised itself as a massively parallel processing system, powerful enough to finally make the dream of relational databases a reality. The 1012 part of the name indicated that it could manage a database up to 1 terabyte in size, or 10 to the power of 12 bytes. Teradata became successful, but their computers were known for being expensive. So when Netezza debuted its first product, it was advertised as an affordable appliance for business intelligence. Like Teradata, it used a shared nothing architecture with parallel nodes. But instead of using a proprietary database like Teradata, it was based on the open source Postgres database, and it ran on open source Linux. So it was less expensive. My talk at this conference last year was about Hadoop, so I won't spend a lot of time rehashing. Suffice to say that when Doug Cutting was working on his hobby to index the internet by using a homemade grid of old desktop computers, he could not afford a Netezza appliance. So Doug used Google's published research to build a parallel distributed processing framework. What makes Hadoop especially different from Teradata, Netezza, and Exadata is that Hadoop was not designed to process structured data like you find in their relational databases. When Oracle introduced Exadata, it sounded a lot like Teradata in that it was a machine that could run a large database. But instead of terabytes, Oracle promised a machine that could run a database which contained a petabyte of data. When it debuted, it was named the HP Oracle Database Machine. Only its special storage tier was actually called Exadata. Then 6 months later, Oracle announced that it was purchasing Sun Microsystems. So 6 months after that, Oracle started calling it the Exadata Database Machine made by Sun and Oracle. Sorry, HP. We can't leave the 1940s without mentioning Grace Hopper, one of the greatest designers of programming languages. One of the languages she created became the basis for the COBOL that we still use today on our mainframe. Mainframe is a funny word, right? We say it as one word today, but it used to be two. Early computers contained a massive amount of large components, like these vacuum tubes, which were held together by building wooden frames around them. Just like how we build frames today to hold up drywall panels. The frame that held the CPU was called the main frame. Anyway, these tubes gave off a lot of light, so they naturally attracted insects. While Grace was troubleshooting, she found that the root cause was a dead moth trapped inside one of the frames. An operator taped the moth to this logbook and made an entry. First actual case of bug being found. Afterwards, they all talked about how they debugged the machine, which later morphed into debugging a computer program. The 1950s saw computer usage expand from colleges and the military into the business world. And electronics were still being marketed for how much they benefited your children. Transistors were one of the most important inventions in history. Fortunately, Bell scientists recommended sharing the technology, and they held a transistor conference. 40 of the attendees each paid a $25,000 license fee to gain access to the technology. Whirlwind used 5,000 vacuum tubes, and an effort was started at MIT to redesign it to use transistors. The TX0, or Transistor Experimental Zero, was one of the first computers built with transistors. Whirlwind was also the basis for a defense system, IBM's semi-automatic ground environment, which was physically the largest computer ever built. It weighed 250 tons. Bell Labs also helped create Sage, especially its Nike missile system. The IBM Sage computer actually became a star in the movies, like Voyage to the Bottom of the Sea, and in TV shows like Lost in Space and The $6 Million Man. All of this exposure helped make computer programming a popular career. In 2001, A Space Odyssey, the bad guy, Hal, is a computer with AI skills that controls a spaceship's operations. Spoiler alert, Hal goes berserk and tries to kill the crew. IBM Sage wasn't shown in this movie, but people speculated that Hal's name was a negative reference to the giant computer maker, because each letter in HAL comes one letter before each in IBM. HIABLM. Sorry, IBM. Let's switch gears for a while from hardware to software by talking about levels of abstraction. What if I asked you to draw a picture of me and I gave you this photo to reproduce? This would be a difficult task because the photo is very detailed, so it would take a long time to draw. What if instead I gave you this cartoon to reproduce? It does abstract away some of the details from the original, but it's still similar, so it wouldn't be that much easier to draw. Now, how about this? You could reproduce this, right? The underlying details have been abstracted away, making it much simpler to draw. So how does this apply to software programming? Let's take a look. This is machine code. It's what a computer understands, and it's how we used to write programs. The first two instructions tell a computer to store the number 10. The next two instructions tell it to store the number 20, and the last four instructions tell it to add 20 to 10. Needless to say, this wasn't a very efficient way to program, so we tried to make things a little bit easier. This is assembly language, and these instructions perform the same operations as our machine code. So it's a little easier, but we're still dealing with registers, memory addresses, and call stacks. Assembly language and machine code are called low-level programming languages because they provide no abstraction from a computer's hardware. Programming is much easier today because we created a higher level of abstraction. This looks like modern programming, right? These three lines of code perform the same operations as our machine code, but with a strong abstraction from the hardware details. After seeing the low-level alternatives, I never again complained about having to learn a new high-level language. Speaking of programming, let's take a break from this decade and look at functional programming. Alonzo Church created lambda calculus as a way to express computation with functions. Lambda calculus influenced the design of the Lisp programming language at MIT, and it quickly became the favorite language for AI research. Lisp is short for list processor. Scheme was created at the MIT AI Lab, which was later relocated to this really cool building. Scheme improved on the functional aspects of Lisp. This is Java's mascot, and he's busy sculpting a lambda. Here's a simple lambda expression that converts a list of strings into a list of string lengths. Scala is a higher level abstraction of Java. So here, the Scala mascot has the easier job of simply painting a picture of a lambda. So the Scala lambda expression is easier to code. Hadoop's MapReduce is distributed Java, and Spark is simply distributed Scala. But Scala's higher order functions make writing Spark code so much more efficient than writing MapReduce. Word count is important to apps like search engines because the most frequently used words are usually the least relevant in terms of search indexing. For comparison, here's a MapReduce program written in Java that finds the top 10 most frequently occurring words in a document. I had to squish all the lines together just to make them fit onto one slide. Now here I wrote the same kind of program for Spark, but with just one line of Scala code. Have I told you how much I love Scala? The most useful tip you'll hear today is teach yourself Scala. As strange as this may sound, the first hackers came from MIT's Model Train Club. Most club members just enjoyed creating buildings and landscapes for their trains, but a small group cared more about what happened underneath the train layout. The electronics under the layout were simply called the system. Like other college kids, they had their own slang and even kept a club dictionary. Here are some of the words that they used. Of interest to us is the term hack, which is a project that you're excited to work on because it tests your creativity. When they said that they were hacking the system, it meant that they were exploring creative alternatives to make it run more efficiently. So they were proud to call themselves hackers. In the late 50s, the team that worked on the system became interested in computers. After they took MIT's Lisp class and got to use the TX0, they extended the term hacker into the programming realm. When we say hacker, we should mean a creative, trustworthy programmer. The hackers at MIT would go on to start the open source movement. Unfortunately, mainstream media corrupted the term hacker to mean cyber criminal. Fake news! Now let's take a look at how programming has changed over the years. Here's what a programmer looked like 71 years ago, programming the ENIAC computer. Obviously, programmers dressed a lot more formal back then. After machine code was written out on paper, the process of getting the program into the computer by plugging in its cables could take weeks. Initially, programs were read into Whirlwind via a punched paper tape. Punch cards were about the size of your hand, and they replaced punch tape. The largest program ever punched onto cards was for Sage. The main program was stored on over 62,000 punch cards, equivalent to about 5 megabytes of data, or about the size of one iPhone photo. This photo shows how handwritten programs were transferred onto punch cards by key punch operators. Speaking of 5 megabytes, this is IBM's first hard drive. It weighed 1 ton, cost $50,000, and could store 5 megabytes of data. In comparison, you can buy a 4 terabyte hard drive today for $100, which means 5 megabytes now cost less than 1 penny. Plus, you can get free shipping with Amazon Prime. But I digress. Connecting an electric typewriter to Whirlwind proved how useful a keyboard input device could be. The first mouse was built 53 years ago, and it was named so because the cord attached to the rear looked like a tail. The mouse consisted of a wooden shell, a circuit board, and 2 metal wheels that came into contact with the surface. The first Xerox product sold as a home computer came with a mouse. The girl on the right is blocking our view of the mouse, but she's also blocking something else. What's that by her legs? Oh, snap! That's the actual home computer. It looks like the mini refrigerator from my college dorm room. Virtual reality may be the future of computer programming. This is a VR live coding environment, which enables a developer to edit a program while it's running. And those flying birds represent tweets streaming in from Twitter. The 1960s saw the first use of computers in space. And just look at how portable electronics had become. An increase in the number of people needing access to computers led to experiments in time sharing. CTSS was developed at MIT, and one of its first apps was an email program. Email was first used in time sharing systems. My first company email address was my TSO ID, TJB6589, and I could only use it to communicate with our employees who used our mainframe's time-sharing option. ARPANET started using the @ symbol for its networked email addresses. Then, in the 1990s, after the World Wide Web matured, I became tbertucci@company.com and could email outside the company and receive spam on a daily basis. Bell Labs collaborated with MIT to create Multics, an ambitious project to create the next-gen time-sharing OS. They wanted to create a more streamlined version of CTSS. However, after 5 years of work, AT&T got frustrated with the lack of progress, and Bell Labs was forced to withdraw from the project. This was the video game that started the open source revolution. It was called Space Travel, and it simulated voyages within Earth's solar system. A Bell programmer had created the game on the mainframe that they were using to create Multics. After they had to leave the Multics project, Bell programmers still wanted to play the game, so one of them converted it from assembly language into Fortran to port it from the mainframe to a mini-computer at Bell Labs. He then began writing a small, basic operating system that could simply host the game. The name Unix was suggested because the OS was an emasculated version of Multics. It was only capable of running the game. Later that year, a modified spelling was suggested with an X ending, and the name stuck. AT&T was a monopoly back then, and the US government let them operate as such after a decree that forbid them from engaging in business unrelated to telephones and telegraphs. Since Unix was neither, Bell Labs could share its source code with colleges, and Unix was created in a collaborative manner. Another major breakthrough in the 60s was the guidance computer for NASA's Apollo spacecraft. MIT researchers worked for years to reduce the computer from the size of 7 refrigerators to a compact unit weighing only 70 pounds. The movie Hidden Figures was about human computers who worked on the Mercury and Apollo programs. When they saw that NASA purchased an IBM mainframe to replace them, they taught themselves how to program in Fortran and became NASA's first programmers. This is exactly the kind of spirit that permeates open source programming. We are self-taught and self-sufficient. If you haven't seen this movie, I highly recommend it. Very inspiring. The 1970s saw the birth of companies that would grow into the wealthiest corporations in history, like Apple, Microsoft, and Oracle. And men wore belted sweaters in the 70s. Unix evolved rapidly, and Bell Labs released the first Unix programmer's manual, introducing the now famous man page format. It's been mansplaining ever since. They also created the C programming language just to make it easier to port Unix to other computers. C has since become the most widely used programming language of all time, and this concisely written book has spawned generations of new programmers. Speaking of Unix, let's take a look at some other operating systems. The Atlas Supervisor was a program that managed resource allocations for Manchester University's Atlas computer, and it's considered to be the first modern operating system. Atlas was one of the world's first supercomputers, and it could process about 1 million instructions per second, what we now call 1 megaflops. In comparison, supercomputers today compute at about 100 petaflops, or 100 quadrillion operations per second. Now that's a lot of flops. The first Unix system was created at Bell Labs, and many Unix clones followed in its footsteps, like IBM's AIX, Hewlett-Packard's HPUX, and Sun Solaris. After Steve Jobs was forced out of Apple, he started a company named Next, which created a Unix clone named Next Step that ran on a workstation named Next Cube. Apple's Mac operating systems were named like OS 8 and OS 9, but then Apple purchased Next, rewrote their OS based on Next Step, and named it OS X, with a Unix-like X ending, which they told everyone was to be pronounced OS 10, but everyone just calls it OS X. Which is interesting because recently Apple introduced iPhone X, and they call it iPhone 10 in their commercials, but everyone just calls it iPhone X. Apple released the core operating system components of OS X as open source software named Darwin, but they kept the higher level APIs closed source. iPhone OS was a mobile operating system created by Apple for its hardware, like the iPhone, and then later the iPod Touch and iPad, so they eventually renamed it iOS. It's based on Darwin, so it traces its roots back to Unix, making it easy for developers to write all those apps for it. The arrival of the IBM PC in the 80s transformed computers from business tools into personal computers. You see, up to this point, IBM was the largest computer maker in the world, but they sold the big time-sharing computers that you used at work. Now just imagine, you could have your very own IBM computer at home, a personal computer, no more sharing. When the Ma Bell monopoly got broken up into Baby Bells, the old decree no longer applied. So AT&T began selling Unix as a commercial product. So to the open source community, Unix became something to fight against. It was no longer a platform for collaboration. Richard Stallman quit his job as a programmer at the MIT AI lab and started the GNU project to free Unix, with the goal of creating an open source Unix clone. So what does it mean for software to be open source? It's probably easier to define closed source. I created these slides using PowerPoint, and when I got my PowerPoint license, I got access to just the executable app. I didn't get access to the source code from the C programs used to create PowerPoint, so I can't read the code to learn from it or to customize it. So when we say that open source software is free, we mean that you have the freedom to view its source code. Sure, today's open source software can often be downloaded for free, but that wasn't the motivation behind the revolution. As Stallman would later say, it's free as in free speech, not free beer. I mentioned that the name of the open source Unix clone is GNU, which sounds kind of silly, so let me explain. MIT has a tradition of naming software by using an acronym that refers to itself. For example, after they created a text editor named Techo, they created an improved version named Tint, which stood for Tint is not Techo. After they created an editor named Emacs, they rewrote it in Lisp and named it Ein, which stood for Ein is not Emacs. Then they improved Ein and called it Zwei, for Zwei was Ein initially. Clever hackers, Ein and Zwei mean 1 and 2 in German. So now you know why Stallman called his Unix clone GNU, because GNU's not Unix. He also insists on pronouncing it with a hard G. That's why I keep saying GNU instead of new. GNU became a collection of Unix-like utilities, but the project was not successful in creating a Unix-like kernel. The kernel is an operating system's core program, and it has control over the hardware. One of the most important achievements of GNU involved copyright law. The GNU General Public License was a big innovation, and it's very different than a standard copyright. GNU coined the term copyleft, and it ensures that open source code remains freely available even if it's used to create other software. Now let's take a look at open source based businesses. Cygnus was the first company to provide support for open source software. Their name was a recursive acronym which stood for Cygnus, your GNU support. Red Hat got its name from the fact that the company's founder frequently wore a red Cornell University lacrosse hat. Red Hat merged with Cygnus and they distribute a popular Unix clone today. When Netscape was founded, their goal was to overtake Mosaic as the most popular web browser. So the internal code name for their browser was Mozilla, which stood for Mosaic Killer. At its peak, Netscape had 90% of the browser market, but eventually lost out to Microsoft IE. In a last-ditch effort to regain market share, Netscape open-sourced their browser and started the Mozilla Foundation 14 years ago, which created the Firefox browser. Fun fact, the name Firefox is a nickname for a species of red panda bears, which happen to look like foxes. So the animal on the Firefox logo is actually a bear. Similar to how companies like Red Hat distribute open source Unix clones, some companies distribute open source Hadoop software, and Cloudera is one of them. As their first website here shows, when they started, they did not have software to distribute. They could only help you install and maintain an Apache version of Hadoop. Today, they sell a commercial distribution of Hadoop, similar to other companies like Hortonworks and MapR. Databricks was founded by Matei, the guy I mentioned earlier who created Spark. Databricks is like a Cloudera, but only for Spark, not the rest of the Hadoop ecosystem. They make money by hosting their own cloud-based Spark platform on Amazon Web Servers. They also have a free community version, which I use at home for its tutorials like the one shown here. Confluent is like Databricks, but for Kafka instead of Spark. Kafka is a distributed pub/sub system that's optimized for writing, so it was named after writer Franz Kafka. Kafka is based on a simple idea, and I'm going to use a Netflix analogy to explain it. When Netflix publishes new episodes of a TV show, they don't email each episode to all of their subscribers. They just add episodes to the end of the show's list, and then each subscriber can start watching them wherever they left off. So it's up to each subscriber to keep track of their position in the list. The publisher just writes new content. In the 1990s, the rapid growth of the World Wide Web changed communication forever. Speaking of communication, my boss still sends me messages like this. Watch your back. The open source revolution hit another gear when a college freshman at the University of Helsinki decided to write a Unix clone for his PC. It mattered that he lived in Finland, far from the center of computer research. He couldn't speak with many developers locally, so the web served as a lifeline for exchanging ideas. He was just trying to make a kernel for his PC, and he didn't intend for anyone else to use it, so he only asked a friend to post its source code online to solicit feedback. His name is Linus Torvalds, and his secret code name for his hobby project was his first name, but with a Unix-like X ending. He had intended to call the OS Freaks, which was the word freaks, but with a Unix-like X ending. Remember, he was just a college freshman. But his friend didn't know about the freak's name, so he posted the code to a directory named put/os/Unix, and the world came to know of it as Unix. GNU's mascot is a wildebeest, which is also called a gnu pronounced with a silent G. The Linux kernel's mascot is Tux, which is short for Torvalds Unix. When Linus adopted GNU's license for Linux, GNU saw this as an answer to their prayers for a kernel, so they combined their Unix-like utilities with the Linux kernel to create a GNU Linux operating system. GNU software actually accounts for 10 times as much of the OS source code as the Linux kernel, so it does make sense to call it GNU Linux, but hardly anyone ever does. And no one has really accepted this monstrosity as the GNU Linux mascot. There have been about 1,000 different Linux distributions, but only a handful are really popular, and here's an example of 3 of them. Debian was one of the first, and it received support from GNU because its founder, Ian Murdoch, called it GNU Linux. The Debian name came from combining his girlfriend's name, Deborah, with his own name, Ian. SUSE was created in Germany, and its name is an acronym for Software und Systementwicklung, or Software and System Development if you don't sprechen Sie Deutsch. Ubuntu is based on Debian, has a very nice GUI, runs on a lot of PCs, and on more than half of all Amazon web servers. It's named after the African philosophy of Ubuntu, which means humanness. The big event of the 90s was when Tim Berners-Lee created the World Wide Web. This is what the first web page looked like. If you look close, you can see that he created the web's components on a Nextcube using the NextStep operating system. Berners-Lee invented HTML, a server that serves HTML, a browser that displays HTML, and HTTP, which allowed communication between servers and browsers. A few years later, a group of developers began collaborating to build a better web server. Their development relied on a series of patches to the original codebase. So they called their web server a patchy server, which became Apache Server. Then a few years later, the group formed the Apache Software Foundation to provide support for the Apache server. Then they started to host other open source projects, and Apache is now an umbrella organization over about 400 software packages like these examples. The Apache server was the software that made Linux a must-have operating system. These 2 open source packages, combined with 2 others, a relational database and a scripting language, became known as the LAMP stack. And it was this open source software bundle that built the web. Okay, one last 6 degrees graph. Fortran is short for formula translation, and it was created by a guy who said he was just too lazy to write in assembly language. It was the first widely used high-level language and is still used today, especially with supercomputers. You may have wondered why C was named C. It's because the C compiler was written in B. B was a stripped-down version of BCPL, which stood for Basic Combined Programming Language. And C was written by the same guys who wrote B. SAS was written in C, and I don't know how this slide got in here. I must have been hacked. Fake news! S was written in C and created at Bell Labs. They wanted to call it Statistical Analysis System, but that name was already taken a few months earlier. So in honor of C, they named it S. Python was written by a Dutch programmer who was looking for a hobby that would keep him busy during his Christmas vacation. It was named after Monty Python, and my kids learned how to use it in like 3rd grade, so it must be pretty easy. R is awesome. I created this map with R. R was based on S and written in C. It was created by 2 guys whose first name begin with the letter R. Ross and Robert. So, in honor of themselves and in honor of S, they called it R. And lastly, according to my map, you should probably hold on tightly to your wallets and purses as you exit the auditorium. Thank you.